Hello, my name is Logan Richards, and I'm going to be presenting my long term from this year where I compared optimizations to a backtracking algorithm intended to solve Sudoku puzzles. So here's a little background. Backtracking is an algorithm used within the field of computer science, and it is mainly used with problems that a brute force method would take an extremely long amount of time to do because there are so many permutations of the solution that you can't do that method. So backtracking works by adding pieces to a potential solution and evaluating whether that piece negatively affects it. If it does negatively affect the solution, it's thrown out and a new piece is evaluated. Otherwise, the piece is considered correct for the time being and the algorithm moves on to the next piece that it needs to solve. If that path is then found out to be incorrect, it goes back to that original piece and tries a new one. So here's a visualization that I made for a Sudoku puzzle while it's being solved with a backtracking algorithm. So as you can see in the top left, there's a 2 there right now. So the current guess in the top left corner is 2. And it's going to continue guessing new numbers. And it found out that the path of 2 was incorrect, so it changed it to 3. And it continues to do that all the way down to the bottom right corner. So after it finds out that 3 is incorrect, it is going to change it to 4. And then from there it solves the puzzle. So, and the white squares are the squares that were originally given with the puzzle. So for my procedure, I compared 2 different optimized algorithms with the original one over 100 Sudoku puzzles. So the algorithms were sequential guessing, which was the original, where the guesses started at 1 and they increased in order up to 9. Randomized guessing, where each slot, the sequence of guesses was randomized, and then a frequency-based guessing algorithm where the guesses are based on how many times a number appears in the original puzzle. So for instance, the first guess would be the number that appears the lowest amount of times, and the last guess would be the one that appears the highest amount of times. So my claim was that the frequency-based guessing algorithm would have a faster solving rate and the smallest average number of guesses per slot. And the reason I thought this was because it was really the only algorithm that was using probability and statistics to decide what guess to make, rather than just either randomly doing it or keeping it constant the entire time. So here is the main solving function that I wrote. The rest of the code is linked later in the presentation, but this is the main function. So it takes an unsolved Sudoku board and it solves that while it keeps track of the number of guesses made. So the first few lines, starting at board equals i.copy, it is making a copy of the input board argument, and the reason I need to do that is because if you don't, you have a reference to the original object in memory. So if you would make any changes to it, you're actually changing that original object. So to keep that from happening, you have to make a copy of it. And the next lines are just getting the location of the first empty square. These new lines here are making a copy again of the sequence, and we're doing this for the same reason, and then shuffling if I am testing the random algorithm, but if not, it just keeps the sequence as the original. The for loop here is looping through the entirety of the sequence and making sure that the added value doesn't cause any errors. So where it says check equals checkboard, that is checking to make sure that the new added value does not cause any errors within the puzzle. And then if there are no errors, it's going to continue to recursively call this same function here until the puzzle is eventually solved. And each time it calls that recursively, it's calling the updated version where there is a new value in there. And then eventually, when the board is solved and it's input into the function, it just returns the original board with the number of guesses that were made. So here are my first results where I compared time versus the number of puzzles solved. So I did 3 trials for each algorithm. Blue was sequential, red was random, and green was frequency. So as you can see, it sort of turned out how I expected, where the frequency model was performing better than the original, but I did notice these spikes at around 50 and 80, and when I looked further into that, I realized that those puzzles actually had more empty squares, which just meant that they were going to take a lot more time than the other ones. So I decided to ignore these spikes because it happened in every single algorithm. And then the other thing I noticed was that the random-based guessing algorithm was performing very poorly. And I noticed there was a large difference in time between that and both of the other algorithms. So I looked into it and found out that this was due to the shuffling of the sequence. So originally the sequence of guesses was 1, 2, 3 up to 9, but it had to change into a random one, and that takes a lot of time. So instead of comparing the time, I decided to compare the number of guesses for each algorithm, so I can compare them in a better way. So this was that graph. So as you can see, it's similar because it's another linear pattern, but in this case, it performs closer to what I imagined it to be, where the random algorithm performs better than the sequential at some times and then worse at others. So from like 20 to 60-ish, random is performing worse, and then 60 to 100, random is performing a little bit better than sequential. But I had a big problem with this because it was really hard to compare the sequential guessing algorithm with the other two optimized ones, just because of the way I represented the data. And since I wanted to focus more on how those optimized algorithms differed from the original, I decided to take the averages of the sequential guessing algorithms trials and plot the differences from the optimized algorithms averages. So what that looks like is this. So anything negative means that the random or frequency-based algorithm was performing better than the sequential, and anything positive means it was performing worse. So in this case, they both performed better for the entirety of the amount of the 100 puzzles, except for a period around 70, where the frequency-based guessing algorithm performed almost exactly the same. And I noticed something odd where the random-based guessing was actually being more effective after around 50 solves, and it was performing better than the frequency-based guessing. And I thought this might be a fluke because up until then it seemed like the frequency-based guessing was performing the best. So I wanted to test this over a larger number of puzzles. So I decided to use 1,000 puzzles rather than 100. And when I did this, again, positive means it's performing worse than the original algorithm, and negative means that it's performing better. And after I did this, I noticed that after around 50 to 100 puzzles, random was performing either the same or better than the frequency-based guessing algorithm, except for an area around 200 to 300. And I took the averages of those values, and random-based guessing was actually performing around 2,200 guesses better than the original algorithm, and the frequency-based guessing algorithm was actually, on average, performing around 500 guesses worse. So this led me to the conclusion that the random-based guessing, first of all, was the worst when comparing the time, but this was only due to the shuffling of the sequence in the algorithm. And then the frequency-based guessing algorithm had the fastest solving rate and the lowest number of guesses per puzzle only when you were evaluating a limited number of puzzles, so around 50 to 100. But then after that, based on my data, it seemed like the random guessing algorithm became more efficient than the frequency-based guessing algorithm. And then here's my link to the original source code. I didn't use Replit for any of the testing. I used a free IDE called PyCharm. So some of the components might not work in Replit, but I wanted to give a link to the full source code, so that way if you wanted to look at anything or ask any questions, you could. Thank you. Any questions?